Okay, so good day, grade 8 Mathematics Science High School students. Okay, so for our first lesson, we're going to be discussing about basic proportionality theorem. Okay, so the basic proportionality theorem came into origination or originated in the time of Thales of Miletus. Okay, so that was from 624 to 544 before the Common Era. Okay, so it was one of the great Thales of Miletus was one of the great mathematicians and philosophers of his time. One of his contributions to the field of geometry is the basic proportionality theorem, or also known as the side splitter theorem. Okay, so it's not to be confused with Thales's circle theorem. Okay, so he has another theorem about circles. So this one is our lesson will be mostly focused on Thales's basic proportionality theorem. Okay, so when Thales visited Egypt, he observed that Egyptians always measured vertical angles to see whether they were equal whenever they created two intersecting lines. So Thales concluded, okay, from out of these vertical angles, he created a proportionality theorem that says that this segment right here, okay, so let's say for example we have A, B, C, D, E here. So he came up with a proportion that says that AB over BC is equal to, okay, EB over BD. Okay, so that's one of the proportions that Thales created. Okay, so Thales's basic proportionality theorem can be shown by the given figure below. Okay, so this is the figure that we have here. Okay, so the basic proportionality theorem or the side splitter theorem states that DE here on this figure, okay, so DE over BC is equal to AE over EC is equal to AD over DB. So the proportion or the ratios of these side measurements that have been cut or have been bisected or cut by different lines, so they are congruent to each other. Okay, so their proportions or their ratio. The basic proportionality theorem states that if a line intersects two sides of a triangle, we have your triangle ABC. Okay, triangle ABC. So therefore, if a line intersects two sides of a triangle and is parallel to the third side, so the line there that's parallel to the third side would be line segment DE. So therefore, then it divides the first two sides proportionally. So that means, as we've written here, AD over DB is equal to AE over EC, which is also equal to the proportion of the parallel sides. As you can see also from the given figure, we could also then conclude that AD over DB is equal to AE over EC, the one that we've concluded from the previous slide. Okay, so let's try to prove this theorem through a very practical example. So given a lamppost R, okay, so it kind of looks like a sun, but it's a lamppost. Okay, lamppost R with rays RA and RS. The two rays intersected the road at points A and O for row RA and points D and S for ray DS. So to prove the converse of the basic proportionality theorem, that the line segment OD is parallel to AS, then we must construct a line AC on the figure over the road. Therefore, we have, okay, so if you construct a line segment AC, we'll be able to prove that line segment OD is parallel to line segment AS, and that proves the converse or the opposite, or yeah, kind of like the opposite of the basic proportionality theorem. So since we cannot directly prove that OD is parallel to AS, we created a line segment AC such that it is parallel to the third side, which is AS. Okay, so we can write that as our first statement that we have here. Okay, number one. Okay, so we can write here OC. Okay, OC is parallel to OC is parallel to AS. So that is an assumption. Okay, so we can write this an assumption. And number two, okay, number two we can state here, and number two that. Okay, so therefore we can state that RO Okay, we can write here that RO over OA is equal to RC over CS. Okay, so the reason for that is, of course, the basic proportionality theorem. What we want to prove here is the converse of the basic proportionality theorem. So that's why we can use this specific reason, okay, for this proof. Okay, so let's see the okay, so for our third statement, we can write here the given itself. So RO over OA is equal to RD over DS. Okay, so that's simply going to be given. Okay. And for our fourth statement, we can number 4. Okay, so using statements number 2 and 3, we can write here that RC over CS is equal to RD over DS. Okay, RC. Okay, so let's write that neatly. Okay, so RC over CS is equal to RD over DS using the transitive property of equality. Okay, so let's write that. Okay, so that's from statements 2 and 3, right? Transitive property of equality or congruence. Okay, so that's from statements 2 and 3. Okay, for our fifth statement, we can write. Okay, so for our fifth statement, we can write here. Okay, so we can copy the fourth statement, okay, and paste that here. And for number 5, we can say that we want to add 1. Okay, so we want to add 1 on both sides. And if we're going to add 1 on both sides, okay, so the reason for that is simply the addition, okay, the addition property of equality. Addition property of equality. Okay, so the statement here, okay, for number 6 is going to be, okay, so the statement, okay, so let's simply copy this one, okay, and paste it here. But instead, what we're going to have here, okay, for number 6, we're going to have RC, okay, RC plus, okay, plus CS all over CS is going to be equal to, okay, it's going to be equal to RD, okay, RD, okay, RD plus DS, okay, RD plus DS all over DS. Okay, so that's simply, you know, the reason for that will be simply simplification of the addition of the plus 1 that we have there. After that, we're going to write, okay, so for number 7, we can write here that, for number 7, okay, so we can write here that RS over CS is equal to RS over DS. Okay, so there you go. Because what we did here is we substituted, okay, the value of this line here. If you guys see this line, okay, I'm gonna draw it in black, this one. RC plus CS, okay, so it gives you RS. And also RD plus DS, so that also gives you RS. So the reason for that is simply substitution property, okay, property of equality. Okay, and for our 8th statement, okay, for our 8th statement, we can write, okay, for our 8th statement, can be written that CS is equal to DS using the division property of equality or and multiplicative inverse. Okay, and for our 9th statement, we can say that, okay, so since CS is congruent or equal to DS, so we can also say for number 9, okay, number 9, that points C and D are the same, okay, because it can be reflected by the symmetric property of equality. Therefore, we can say here on number 10, okay, so number 10, that line segment OD is parallel to AS. Okay, so the reason for this one is by using our assumption on number 1. Okay, so this is going to be the substitution property of equality based from statement 1. Okay, because we've substituted from OC, it became OD because we said that point C and D are the same or are equal to each other. And therefore, we've proven the converse of the basic proportionality theorem. Okay, for this one. Okay, so theorem, if 3 or more parallel lines are cut by 2 or more transversals, then the segments cut off along the transversals are proportional. Okay, so that's one of the main facets of the basic proportionality theorem. So let's try to prove this theorem. Okay, so we can write here for number 1. Okay, so we can write here the given dy and er are parallel to each other. So that is simply a given. So for this problem, guys, we would like to prove, okay, we would like to prove that dA here, dA over AE is equal to yn all over nr. Okay, so their proportions are the same, or the ratio. The ratio of dA and AE is equal to the ratio of yn and nr. Okay, so let's try the second. Statement. What can be our second statement for this problem? Okay, so for the second statement, we can write here. Okay, draw a line dr. Okay, so the simple reason for that would be 2 points. Determine a line. Okay, and then we can also write here. We can write here for number 3. Let point S be the intersection. Okay, the intersection of lines. Okay, of lines dr and an. And the simple reason for that can be 2 intersecting lines have 1 point in common. Okay, so for this problem, guys, you will notice two proportions. Okay, so for this one, we can derive 2 proportions. Okay, for this one, okay, for this figure right here, and for this figure right here. So that's the first proportion, and the other one would be, let's use it on a green tone. Okay, this proportion right here and this proportion right here. And from there, using the transitive property of equality, okay, we can say, okay, we can now say that this proportion dA over AE is equal to yn over nr is true. Okay, so we can write here for number 4. So dA over AE is equal to ds over SR. And we can also say that yn over nr is equal to ds over SR. So that is only the number 4, the basic proportionality theorem. Basic proportionality theorem. Okay, and therefore we can say finally here on number 5. Okay, so if we have here a third line, so that's going to be dA all over AE is equal to yn all over nr, of course using the transitive property of congruence. Okay, transitive property of congruence, and that's simple. So we've already proven that the ratio, okay, of one side of 2 intersecting lines that have been that had 3 parallel lines passing through them. Okay, so the ratios of those 2 lines are equal. Okay, or the proportion is the same. Okay, and we also have here another theorem. So the bisector of an angle of a triangle separates the opposite side into segments whose lengths are proportional to the lengths of the 2 other sides. Okay, so we have here a paragraph proof. We constructed a paragraph proof, and we've proven that AD over DC, okay, is equal to AB over BC using a paragraph proof for this one. So given triangle ABC with line segment BD, okay, so bisecting angle B and intersects AC at point D. Okay, using the parallel postulate, draw line CE. So we made a construction for that, and we also used the transitive property of equality to prove a certain statement. And from there, by using the substitution property of equality, we can say that AD over DC is equal to AB over BC.